Test. All right, one more test. Okay, folks. One more thing I need to do before I hear an echo. There we go. All right. So thanks for tuning in or watching this later, as you will. Had a couple of technical difficulties that nearly stopped us, and one of which is we're no longer at the original link. So if you're here, glad you found me. Something was up with the stream on the other page, so I'm trying this live stream YouTube feature thing. The other technical difficulty is while I found some new whiteboard software that seems to be, let's put this to the test here, it seems to not lag, oops, nearly as badly. I seem to be writing a little bit better with this. But the problem is, as you can see, it says connection failed. Well, that's that means that it's not going to, you're not going to be able to watch this on your own computer. The way it was going to work was you'd be able to pull up this URL on your own computer and get a full quality stream of the whiteboard at the same time. But right now it's not the server is down. So while I can keep editing the whiteboard, you can't have it on your own computer at the same time. But that's okay. We're going to make this work despite all the bugs. I think we're ready to go. So apologies for the delay. What I want to talk about is the triple integral, and today I've also got my notes up on the stream as well. So we are no longer beginning shortly, we are beginning now. So let's get rid of you. All right. So let's talk about the triple integral. So the triple integral, the way that works, it's a well, let's kind of do an overview of the types of integrals that we've dealt with so far. We have the good old-fashioned single integral. We remember this guy, although we didn't usually call it. We didn't usually go I. We usually would write A to B. But what did that represent, actually? Well, what it actually represented, make that a little bit more horizontal, here we go, is we would take the interval from A going out over to B. We would take this function, f of x, and we would find the area underneath that curve. All right, so we've got that. That's all well and good. But what do we do from there? Well, then we introduce the double integral, which is kind of the same concept. We do it over a region D or R. We have a function of two variables, x and y. We'd integrate with respect to the area A. All right, so the picture there is we would take, instead of my A to B, I now have a region D, and that's some subset of the xy plane. There's my D. And then we would take the function f of xy, and for every point inside that region, we map up how far it goes. And we get this surface right here. And so what we had here was area, and what we have here is volume. So the way I defined, we'll define the triple integral. It's probably what you'd expect. I just need to draw a four-dimensional object. Gosh, that's going to be a hard sell, I understand. But that's what it is. It's a four-dimensional object. Oops, only three of them. So it's a triple integral of a function f of x, y, z dv over a region D. And that's going to be this sort of picture. All right, we're going to have a solid D in 3D land. And we're going to take for every point in this solid, we're going to extend it out by the value of the function. And this is an awful picture because, well, we don't live in 4D world, we live in 3D world. So it's going to be kind of hard to visualize, but it's going to be the four-dimensional hypervolume. And I defined what hypervolume was back in the section 5.3, right? I defined it to be the extension of the previous dimensional hypervolume. Sort of like, you know, area is integrates to volume. Well, volume integrates to four-dimensional hypervolume. All right, well, that's all well and good, but before I go any further, before I even tell you how do I compute this, I better give you a good reason to care, right? Because areas and volumes are real. Four-dimensional hypervolume, maybe that's a harder sell. Maybe that's something you don't care about just yet. Well, let me give you some applications before I go any further. I'm going to give us some applications for the triple integral. Okay? So, first things first, I'm going to give you two applications that we're familiar with. All right, because of the same applications I gave you for the double integral, just now they work for the triple integral. So remember how the double integral of the function 1 with respect to area, that gave you the area of the base D. Well, if we're talking about a triple integral instead, that's just going to be the volume. So that's our first application here. This gives us another way to find the volume of a three-dimensional object. Remember that this is a little bit different. It's a subtle thing, but remember, if you want to find the volume of some objects, you can also do the double integral of f of xy dA That works sometimes, I should say, right? That worked back up here. That's one way we can get volume. But the problem with using that all the time is that the base has to be the xy plane. Okay? That's kind of a major restriction there. With the triple integral, so let me erase this because you can also use that to find volume, but it's not quite as useful, right? With the triple integral, what are we doing? Well, we're in 3D land. We have our region D in 3 dimensions. All right, I want to find the volume of this jelly bean thing. Okay, well, what I'm actually doing is finding the hypervolume. I'm extending each point by 1 every time into that 4th dimension that I can't even really draw, but I'm trying my best anyway. But yeah, what is hypervolume of if your 4th dimensional width is always 1? It's just the volume of the base times the height of the 4th dimension. So that's the idea there. We're going to get the triple integral is going to give us a clean way to get the volume of any region as long as we know how to set up the triple integral. And we'll talk about how we set those up later. Okay, so that's one application. What else do we got? This would be a good time to check to see if I have any questions on the chat. We have 4 of you watching live currently. So as before, you should be able to, from that link that I sent you, chat live. I say chat live, but remember there is going to be a delay of about a minute. So whenever I stop and look for questions, it's best just to type them along the way whenever you have them, and I'll turn around every once in a while and check to see if they're there. And if they pop up, then I'll try and address those when I take these breaks. But I'm going to have to, at least for this first time, stall for about 60 seconds. I think I've chatted enough. I don't see anyone chatting, so just add your questions to the chat whenever you have them, and I will answer those as best as we can. And all right, let's keep moving. So that's our first application. You know, however the heck we evaluate this triple integral, it's going to tell us the volume. So we'll have to figure out how to do that in a moment. But for now, let's talk about another application. Well, talk about the average value of a function. So if we take the volume of the region D and divide it into the triple integral of a function, that's going to be the average value of the function over the domain D, over the region of integration D. I don't have a great picture for this, but it's the exact same thing that we had a week ago, only then this was area, and we didn't have one of these triple integrals, and we didn't have one of these variables, and this is an area, right? It was the exact same thing as that, but now we have a third variable, so we have a third dimension involved. So that's another application. But I imagine you guys have taken a physics course before, and maybe you want something tangible that you can feel, you can grab and take hold of. All right, so let's talk about my favorite application of the triple integral. Let's let rho, so it looks like a P, but it's actually the Greek letter rho. Let rho of x, y, z be the density at the point, density of the object at the point x, y, z. All right. So let me draw a picture to go with that. And the way I will draw this is I'll have some of the object be drawn in blue. All right. And then I'll have the middle of it be drawn in purple. And then I'll have the last of the object be drawn in kind of a reddish color. Okay, and so this is my attempt at this picture is to let's say red is more dense. And let's say blue is less dense. Okay, so that's the deal here. What would I care about? Well, if I'm talking about density, density is how much mass do you have at a particular point, all right? So I want to figure out the mass, and turns out there's a really slick way to do this. Turns out the mass of the object is the triple integral of the density. And this is the visualization that I have for the triple integral, because I don't think well in 4 dimensions. But that's what kind of mass is. Mass is kind of a 4-dimensional object, and let me explain that when I finish writing the formula. Okay, so the defense of this, why do I think of this mass as a 4-dimensional object? Well, the 3 dimensions of the object are just the points of the object. Okay, for every point in this object, there's a few of them, I'm just tapping them on the screen here. I can identify that point, but there's actually a 4th bit of information. Get that all on the camera. 1, 2, 3, 4. Yeah, a 4th bit of information at every point, and that extra type of information is the density of the object at that point, which I visualized in this picture by the color that I drew at that particular point. So you have 1, 2, 3 coordinates for the position, and then a 4th coordinate tells you the density. And that's all dimensions are. They're just different pieces of information about a particular concept. And so 3 of the dimensions might be spatial, but the 4th dimension, that's a density piece of information. And if you combine all 4 of those pieces of information, that's enough information to tell you the mass. The mass is the sum of those 4 pieces of information, in a way. All right, so that's kind of the way I think of this. A triple integral tells you the mass of an object across the 3D object D with densities rho. Okay. Any questions? I don't see any on the stream here just yet. So we'll keep on moving. All right. Let's see. So that kind of covers all the different applications that I want to talk about. Let's talk about actually how do I compute these guys. Well, the good news is, not letting me select it the way I want it to, but if the thing you're integrating is really simple, if it's just a box, then just like integrating over rectangles were easy, right? Well, integrating over boxes, it's not too bad either. So integration over a box. So here's the picture. So if we got a box, I guess I've been doing in red. So here we'll have X ranges between A and B. Y ranges between C and D. And then Z will range between, I don't want to use F, because I've already used F as the function, haven't I? See, what do I use in the notes? I probably use A1, A2. Let's do it like that. All right, so we have A1 and B1 for X. For Y, we'll use A2 and B2. And then for Z, we'll use A3 and B3. So that's how I've marked it there on the coordinate axis. I guess in purple, I can go and see where these things cross. Okay, so here's the base. I'm going to shade this in. This will actually be important later. But the thing I actually care about is starting up here at the appropriate height. And here's the actual solid of integration up here at the top. All right, that comes from the heights B3 and A3. So I've got this three-dimensional box here, and I can sum this up much more easily by saying it's the product of A1, B1, A2, B2, and A3, B3. And, if you've been paying attention, you're not going to be surprised at all. Just like the double integral, all you got to do is put those numbers on the bounds of integration. So I can do A1, B1 for X, A2, B2 for Y, A3, B3 for Z, and then you have your function, some stuff with X, Y, and Z in it, and then just make sure that they match up. These are X values here, so these ones should go with the X. Okay, and then you have Y for the 2s, and then I'm not sure the colors are really helping here, but Z for the 3s. So they got to match up. Okay, but there's no reason I have to do it in this particular order. Just like with the double integral, the order does not matter as long as they're all numbers. So with a rectangle, the order didn't matter because all the bounds were numbers. Well, with a rectangular box, the order doesn't matter because they're all numbers. So I could do it in a different order. I could put the X stuff here. I could put the Y stuff on the outside. I could put the Z stuff on the inside, the 3s, and that won't hurt a thing. I just have to make sure that they match up. The middles are the X's, the outsides are the Y's, and the insides are the Z's. So how many different ways are there to permute three objects? The answer is 6. So I've drawn 2 of the ways you could set this up. There's 4 other ways to set it up, but I'm not going to write them all out, of course. So on and so forth. I don't care what order you integrate in. If they're all numbers, just make sure they match up. Make sure that maybe this is what I should have used color for. The inside matches with the inside, the middle matches with the middle, the outside matches with the outside. Same thing here. Z goes with 3s, X goes with the first stuff, and Y goes with the second stuff. All right, that's all that matters. So that'll take care of that. All right, so I have an example. Here it is on the notes. Oops. So I'm going to work this example for us. So we're going to integrate a function over a box. We're going to express it as a few different iterated integrals, and then we're going to evaluate one of those integrals. So that's easy enough. So here's an example problem. Does it not look like I took that one from the book? I think the book has a similar problem, but they chose a really wackier thing to integrate. So this one's pretty straightforward. E to the x plus y plus z dv. All right, and I want to integrate that over where d, so evaluate, that's what I'm asked to do, where d is equal to the x has to be between 0 and 4, y has to be between 0 and 2, and z has to be between 1 and 3. Okay? So, all right, well, let's put this to work. Now, the setup is super easy. All right, there's about a dozen different ways I could set this up. So I could set it up as 0 to 4, 0 to 2, 1 to 3. I'm just doing it in order. And then rewrite this. What I'm actually integrating isn't important to the setup of the bounds at all. I just rewrite it as it is. The trick is, well, okay, these were z values, these were y values, and these were x values because that's just the order that they're given in. So the 1 to 3 go with a z, 0 to 2 go with y, 0 to 4 go with an x. Okay? But there's no reason I had to do it in that order. I could do it in whatever order that I want. 0 to 2 maybe. 0 to 4, and then 1 to 3 again. That works fine as well. Rewrite this stuff. So z is still on the inside, but I swapped my x's and my y's. Sure, why not? It's a free country. All the same value, I promise you. Okay? But I don't like either of those. I don't like either of those because I don't like plugging in numbers that aren't 0. 0 is a wonderful number because it's so easy to plug in, but the first thing I have to plug in are 1 and 3, and I'd rather not do that. So I'm actually going to erase all this because the order that I think would be best. All right, you'll go away eventually. Oh, don't need to erase that. That's going to be the same. Okay, the order that I want to do it in is I want to make sure I plug in my not zeros last. So that's supposed to be a 2 if it's not obvious. 0 to 4. And then, so I'm going to plug in, I'm going to wait to plug in my not 0 numbers. I'm going to just push that back as far as possible. So I just need to make sure that it all lines up. My 0 to 2 were y values. My 0 to 4 were x values. My 1 to 3 were z values. Okay. I'm going to stall just a moment, see if there's anything on the chat logs. I don't see it right now. So maybe we're good. All right, I'll keep moving. So, well, that's the setup. How do I evaluate? Well, it's the same way you evaluate double integrals. Bracket off your innermost integral and do that first. Now, in this case, y is my only variable. So y is my only variable. So everything else is a constant. All right. So it's not too hard to see that, well, e to the y plus a constant, its integral, you can do a u substitution if you like, but its integral is just going to be e to the x plus, I'll do that in y again, plus z. That's its own integral. That's easy enough. And I'm going to evaluate this from y equals 0 to y equals 2, because that was my variable at that moment. Everything else just comes on down. 1 to 3, rewrite that, rewrite this. While I'm writing this, let me go ahead and throw out a pro tip to you guys. It's very tempting, because you see all this repetition, I have to rewrite things every single line. Do you really got to do that? And the answer is, yeah. You really need to be doing this. And because remember what you're actually trying to do. You're not trying to figure out the answer. Who cares what the answer is? Some computer can do this so much better than you and I can. Excuse me, can do this. A computer can do this so much better than you and I can. What's important is that you can communicate how it's done. So showing all the steps and all the nitty-gritty details that's what's important to me as the guy reading this, grading your midterm. I need to know that you know what's going on. So you need to show out all the nitty-gritty details. Rewrite. Don't skip steps. You need to show me everything. So I'm going to plug in the top, and I'm going to minus the bottom. And what will I get if I do that? Well, I get e to the x plus z plus 2. Minus e to the x plus z plus 0. And of course I won't bother writing down that 0 because that's a waste of my time and yours. What I will do, however, oops, that one was the lag. Okay. What I will do, however, in order to make my life easier, is I can notice that I can factor out an e squared. I can write this as, I'll use a green color maybe. I can factor this as e squared times e to the, oops, don't want those in that color though. What? There we go. Sorry about that. Well, I'm going to factor out an e squared from that first term. So I got e squared x plus z minus 1 times x plus z e to the x plus z dx dz 0 to 4, 1 to 3. All right, and then I can factor out the e minus 1. I can factor that all the way out, actually, because it's a constant with respect to x and z and every other variable. It's just a constant, some number, right? All right, so I'll factor that all the way out. And I'll have left over 1 to 3, 0 to 4, e to the x plus z. And that just reduces the amount of terms I'm dealing with. There's no reason you had to do it this way, but I think it'll make the next steps a little bit nicer. Okay, well, let's carry on. I need to integrate with respect to x now. It's e to the x plus z, so it's going to be itself again. So keep this in green. So this comes down, blah, blah, blah. 1 to 3 comes down. All right, now got e to the x plus z still. But now I'm evaluating it from x is 0 up to x is 4 dz. So I'll plug in the top minus the bottom. Lo and behold, I've got e to the x plus 4 minus, oh, whoa. Plugged in for x, right? So that's going to be z plus 4 minus e to the z plus 0. Much better. All right. But like a moment ago, I have this plus 4 term here, right? I can factor that e to the 4. I can factor out a 1 from the right term. So by a similar argument to a moment ago, that's going to be the same thing as e squared minus 1 times e to the 4th minus 1. And my leftover is integral from 1 to 3 e to the z dz. Okay. No questions yet in the chat. I'll keep bugging you guys. Please ask your questions. If you got questions, if you're watching this recorded, shoot me an email if you have a question about anything. You can even just say, hey, at the timestamp, what are we at probably now? About 40 minutes in. So at 40 minutes and 26 seconds, I had no clue what you did with that purple e to the 4th minus 1. Can you explain it? And I'll do my best. So feel free to shoot me emails if you have any questions about that. It's not hard to see. You're going to integrate e to the z, plug in top minus the bottom, because you're going to get itself. So the final answer is e squared minus 1, e to the 4th minus 1, e to the 3rd minus e to the 1, which is, of course, just e. And I'm sure you could do something clever. You could factor out, this is what I'd expect for the final answer. If you have a calculator, you can compute it, but, leave that for the computer just to worry about. We care more about, do we know how to do it? If you want, though, you can factor out e from this last term. That gets you e squared minus 1 is left over, so we have 2 e squared minus 1s, e to the 4th minus 1. Heck, you could factor that e to the 4th minus 1 and do even more stuff, but that's getting way too deep into it. This is what I expect right here. So, all right, so that's the general process here. It took us a little bit to get down here. Unfortunately, we didn't get anything that simplified nicely. A lot of times we'll get things that simplify. Just in the questions that I will ask you, they'll simplify. But it's just a matter of doing the thing you've been doing. You just got to do it one more time with one extra letter in the mix. It's the exact same process, though. So there we have that. So it's really easy with the numbers, and that's what you kind of hope to see. If you're integrating a box over a box, it's super easy. You just integrate and plug in numbers, and we're good. So now the question is, well, what if you don't have numbers? What if we have more general regions of integration, as I highlight in my notes here? Well, here's the trick. You can see it right here in the notes. Well, it's hard for me to highlight it because of the way the PDF wants to highlight things. But here we go. Well, that still doesn't work. Oh well. Never mind. The important thing is I can write it on the whiteboard, so I'll write this on the whiteboard. And I'll draw a nice picture to go with it. So here's what you want to see when you're integrating. It's kind of a generalization of the top curve, bottom curve shtick, I should say, that I've been doing for double integrals. So here's the triple integral situation. Here's what you're usually going to see. You're going to have a three-dimensional object. It's going to have a top part, which I'm going to color here in blue, and it's going to have a bottom part, which I'll color here in red. Okay? And the solid is everything between the blue and the red surfaces here. All right? I'll add some more lines in for the red on the front. I'll add some more lines in for the blue in the front. And the important thing here is that we have Z is equal to, if I'm going to match the notes, I think I use gamma. Gamma 2 of XY. And, well, you know, really, I call this the top surface. That's what's important here. All right, and then down here, I've got Z is equal to, I'm going to move that. You'll see why in a moment. I'll write it over here instead. Z is equal to gamma 1, X, Y, and that's the bottom surface. Okay, so that's part of the puzzle. The other part of the puzzle is the fact that below this solid, or maybe even a part of this solid, we have a shadow. Okay, so here is, let's suppose that this is the shadow of that particular region, and I'm going to give it a name. I'll call the overall solid, I'm going to call that D. All right, and I'm going to call the shadow down here, I'm going to call that E. And I'm just going to call that the shadow. All right, and it's a two-dimensional object. You're going to be able to draw it. It looks like we're in the positive XY quadrant, but you're going to be able to draw that same shadow over here in just two dimensions. And usually this is the more important picture. All right, but you're going to redraw it over here. It's the same shadow as before, but now I'm drawing it in just the XY coordinates instead of XYZ space. And here's the trick. If I want to integrate over D, D is a three-dimensional solid, right? If I want to integrate over D, some function f of x, y, z, and it's no longer a box, obviously. Well, how the heck do I set that up? Turns out, glossing over giving you any sort of proof, of course, for the sake of our time, I'll go ahead and get you to the punchline. The punchline is you can take the double integral over the shadow, and then you can do a single integral on the inside. And what do you put there? You put the top surface function of xy on the top. You put the bottom surface on the bottom. All right, we're still going to be integrating f of x, y, z. And since we're plugging in x and y, we're integrating with respect to z. Z is equal to both of those things. And then here, we now just have this boiled down to a double integral. So that will be dA. Of course, you could split this up further. You could find your top curve. You can find your bottom curve. Or you could do left curve, right curve as well. But the way you're going to set up the E here on the outside, that's going to be just set up the way you would do any double integral. And you're just going to base it on the two-dimensional picture of the shadow. So again, this is what's important. We got the shadow that we set up for the double integral on the outside. We got a top surface. And we've got a bottom surface. on just a second. My computer over here went to sleep. Oops. Probably not a bad time to be stalling for questions, of course. If any of you have any, I will see them here on the screen in just a moment. I don't see anything in the chat though, so let's keep going. All right, so let's put this to the test. All right, I've got two examples. Got example 5 here. I'll do that one first. Express the triple integral of x with respect to volume, where w is a solid, where x, y, and z are positive, and wow, okay. So it doesn't ask me to actually evaluate this. Again, I've mentioned this before. My usual trick for the midterm to make the questions short enough to be done within the midterm is to not actually make you compute every single integral that you set up. I may just ask you to set it up. So that's what I'm going to do for example 5. I'm going to set up this solid as a few different triple iterated integrals. Okay, so the fact that there's an x in the middle of it, you know, this guy right here, who cares? Who cares about that x in the, let me blow this up, make sure you can see it, right? Okay. The x here that I'm actually integrating as a part of this triple integral, nobody cares about it, all right? All that matters for setting up the triple integral is the description. It's the solid where x, y, and z are positive, and z is between these two surfaces. All right, so this is set up pretty nicely for us. Let me go ahead and draw the picture to go with that. Okay. So to get that picture, all right, this is example 5. And just so you know what that is, just take a look, you know, down there on your screen in the stream. That's where example 5 is coming from. So here's the picture. Make sure you can get the whole problem there. The picture is, I'm in 3D land, and I'm told that my, first of all, x, y, and z are positive, so I'm not going to draw anything that's not positive for x, y, and z. So I don't need to draw anything in the negative directions for any of those. So that'll make things nice just from a picture perspective. And I need to draw the z values between x squared plus y squared and 2. Well, z is equal to 2 is easy, right? I'm going to go up 1, 2. And that's going to be the plane where z is equal to 2. All right. But what about the whole, what is z equal to x squared plus y squared? Well, that's the usual example that we remember from our Cal 3 course, where we just have a parabola going up in the x and y directions. So I guess that's my bottom surface, so I'll do that in red, like I've usually been doing. So we want this parabola, and it goes around in a circle around the z-axis. But remember, we're only going up to 2. So at z is equal to 2, I'm going to cut it off at that plane where z is equal to 2. So here is my plane, my top plane, z is equal to 2. My top surface, in fact. Okay, and then down here, below it, right here, that is where z is equal to x squared plus y squared. And that's my bottom surface. Okay, so I drew this beautiful, beautiful picture, right? Well, it's all right, but it was also unnecessary because it was kind of obvious. If you look back over here at my notes, it's kind of obvious that z is below 2, So that has to be my top surface. And then if z is greater than x squared plus y squared, that has to be my bottom surface. All right, so sorry, I may have misspoken. Z is below 2, so 2 is my top surface. Z is above x squared plus y squared, so that's as far down as I can go. That's my bottom surface. So I didn't really have to draw the 3D picture, but I don't know what this looks like just yet, but we're going to have some shadow here. Call that E. I'll worry about what the E is in a moment, but I do know for a fact that my triple integral is equal to E integral from x squared plus y squared for my bottom surface, and up to 2. I'll do that in blue to match the picture. What am I integrating again? X? Sure, whatever. So I have some function. It could have been sine of x plus 3y plus e to the z. That has nothing to do with the setup of this picture, but it just happened to be just plain old x. Sure. Now, because my top surface and bottom surface are both z is equal to, that's going to be a dz that goes right here. And I'm going to have a dA out here because I have not set up my double integral for e just yet. All right, but that's the step one. All right, setting up my top surface and my bottom surface, putting those on the bounds of my innermost integral. Now, the hard part of these problems is usually doing the double integrals. So if you can't do double integrals, you're going to have trouble with triple integrals, obviously. But I want to figure out what E is. How does that happen? Well, E is going to happen when the two surfaces intersect. So the trick usually to figure out what your E is just to set the two surfaces equal to each other. Okay? So how do I figure out what E is? Well, I'll draw that picture down here. I know roughly what it looks like because I know what the three-dimensional picture looks like. But to bring the point home, I noticed that, well, it's just x squared plus y squared is less than or equal to 2. I just dropped the z out of this inequality in the notes. I dropped the z, and that tells me exactly what x and y values I care about. I'm just ignoring the z values. So x and y values, x squared plus y squared has to be less than or equal to 2. And that is the equation of a circle of radius square root 2. So here's, I only care about x and y are positive. So here's my circle. And that's square root 2 for the x and the y. Now, I need to set this up for my double integral. All right, this is my E here. I guess I should have done this in purple to match the picture above. All right, so here's my shadow, call it E. Now, how do I do this? Well, it's a double integral problem. So I'm going to find my top curve. Or I could do right curve, left curve. For this one, actually, both of them work. Y is equal to, how do I figure out what y is equal to? Well, I can just solve for my y right here. If I solve for my y, that's going to be 2 minus x squared square root. It's going to be the positive square root because it's on top. For the bottom, it's even easier. That's going to be y is equal to, of course, just plain old 0. Last but not least, what about my values? Well, my leftmost x values are where x is equal to 0. My rightmost x value happens right here at the base. That's where x is equal to square root 2. So there's my left, there's my right value. Here's my top curve, not to be confused with the top surface. And here is my bottom curve. All right, so now I've got the top curve, bottom curve, left value, right value. Well, what can I do? Well, I can just stick it all up here in my double integral. So that's going to bring it home. All right, so from way up here, I'm going to set up my double integral just like I normally would. I'm going to use my top curve, y equals 2 minus x squared. That can't quite read that. 2 minus x squared. And my bottom is a 0. My left and my right x values are 0 to square root 2. And then I still have the brackets unnecessary, but to match what I had written above, I had x squared plus y squared on the bottom. And I go up to just plain old 2 on the top. X is what I was integrating dz. I'm just rewriting what I had earlier. So I rewrite the inside of the brackets down here. But then what about my last two differentials, the dx and the dy? Well, I set it up like a double integral with top curve, bottom curve. So I do it exactly the same way that I usually do. It's y equals for the middle. It's x equals for the outside. So here is my triple integral. And that's it. I was only asked to set it up, so I don't have to do any more work, so that's nice. Was this the only way I could have done it, though? This way worked fine, but you're going to find some problems, like you did with double integrals, where instead of top curve, bottom curve, you wanted to consider right curve, left curve. Well, for this sort of problem, sometimes you're going to want to consider right surface, left surface. Sort of. Let me explain. So here's an alternate solution. All right. Oh, alternate solution, huh? Alternate solution. There we go. What if I had drawn the picture differently? Okay. What if I had, instead of putting the z-axis going up, I'll keep the x-axis here, but let's say I put the z-axis going right and the y-axis going up. So I get the similar picture. It's just that z is now horizontal. So it's over here. Here's z is equal to 2. And then my bottom surface would go up like so, and it'd go up like so. So here is my bottom surface. Well, what was my bottom surface, but now it's sort of like a left surface. And then here was my side, like so. So this is the same picture, but now we've got kind of a different scenario set up here. So what I've done is I've turned things on their side. And sometimes you're going to want to do this because it's going to get you a nicer picture. But how does this work now? Well, it's still top surface, bottom surface. So actually, the top surface, if I'm inside of this solid and I jump up, what am I going to hit my head on? Well, it's actually going to be the red stuff, right? The red stuff is all coming out from the bottom surface. The bottom surface is actually the same thing as the shadow down here. So it's kind of covered up, so I have to, maybe I'll draw it like this. There we go. That seems like a decent enough picture. So the top surface and I'm going to, instead of z equals, I'm going to do y equals. And what is y going to equal? Well, I can just solve for y in this inequality, and I'm going to get the square root of z minus x squared. Positive square root because of the fact that we're assuming y is positive. So the top surface looks uglier, but the bottom surface looks beautiful. That's just the plane where y is equal to 0. So if I set it up this way, I still have my shadow E. In fact, the shadow E is the same thing as my bottom surface. But my top surface, bottom surface equations are now z minus x squared and 0. I'm still integrating x. X, who cares about x? X is just the thing I was told to integrate. It has nothing to do with the bounds of the integral. But because I wrote my y to be my up, so that's my up and my 3D, my top surface, bottom surface, now give me a dy instead. So my triple integral now has a dy on the inside. Okay, now if I set it up this way, then I need to figure out, well, hey, what is the deal here? I want to figure out what my shadow is. That's the trick, right? I need to know how to set up my shadow, E. Okay, well, I'll do that the same way I did it the other way. I'll just draw it in 2 dimensions. But the 2 dimensions now that I care about are the x and the z axes. Okay? Oh, let's see here. So how do I figure out those bounds? Well, I'm going to take where the top surface hit the bottom surface. So basically I'm trying to figure out where the square root of z minus x squared equals 0. But I can square both sides of that, right? Alright, and so I'm going to get that z minus x squared is 0. So that's just going to get me z is equal to x squared. Alright, so I did that scratch work. I can get rid of that now. Alright. So z is equal to x squared. I know how to draw that. That's like y is equal to x squared. So here I have y is equal to x squared. But notice that I have to stop when z is equal to 2. Okay? So what do I got? I've got a top surface, or sorry, top curve now. My curve is equal has to do now that up and down are z. I'm going to use z instead of y for things. But now my top curve is z is equal to 2. But if I'm inside this region, I'm going due south. I'm hitting that red curve. All right, and that's going to be my bottom curve. Z is equal to x squared. All right, all that's left is to figure out my left and right values. And I could have done right curve, left curve as well. There's no reason that I had to do it this way. But notice that my left is where x is equal to 0. And this point right here, my right point, let's see, z is equal to 2. We're on the curve, z is equal to x squared, so it must be the square root of 2. Just set these x squared equals 2, so x equals square root of 2. Alright, so that will get me my final answer. I'll set up my bounds of integration for the double integral. I'll go bottom curve, x squared, to top curve, 2. I'll do left value, 0, right value, square root of 2. And then I'll just rewrite what I had a moment ago. Integral from 0, square root z minus x squared x dy. Now to finish this up, I did top curve, bottom curve, but z was acting like yy, right? So since it's z is equal to 2 and z is equal to x squared, I'll put dz in the middle. Since it's x is 0, x is 0, x is root 2, I'll put dx on the outside. And there is my answer. Okay. So I don't see any questions in the chat log, so nobody had any questions initially, at least, looking at this material. Of course, you may have questions when you've had some time to digest everything. I understand. One thing I should point out is that, hey, what is it? Let's compare this to the other integral that we got a moment ago. So scroll way back up here. Okay, notice that, let's just take, for example, the outside bounds, 0 to root 2. If I scroll back down, I don't believe I ever had a root. Oh, yes, I did. Don't mind me. I don't know what I'm talking about. All right, 0 to root 2 are exactly the same. I'm sorry. Let's pick one that's actually different. We got x squared and 2 in the middle bound. Okay, we scroll back up. I never have an x squared by itself in the first integral that I got. The point being that the whole switching around bounds of integration willy-nilly, however I want, I can just swap these two bounds as long as I swap, oops, that wouldn't make sense at all. As long as I swap these two differentials, that's no good. You can't do that, all right? That's what I ended up having, is I swapped my dy and my dx, but it was a lot more subtle than just swapping the bounds of integration. So in fact, if you want to swap the bounds of integration of a triple integral, you got to do what you did for the double integral. You got to draw the picture and then reinterpret it in a different way, with a different orientation, basically. Yeah, notice that we did not just swap those bounds and these differentials. It was a lot more subtle than all that. That does not work as simply as you want. Now, if they're all numbers, sure, go for it. Those are going to be the same. All right. So, tell you what I'm going to do. We've been at this for about 70 minutes or so. I'm going to call it there. We do have one more exercise, one more example. I think what I'm going to do is I'm going to save that example for after the midterm. What I'm going to do is on Monday, go ahead and just do a review. I think I'm just going to do the review all day Monday. But I might give a quiz at the end on section 5.4, not what I did today, but what I did on Wednesday this week. So be prepared for a quiz on 5.4 at the end of class on Monday. But before that quiz, I'm going to do a review of asking over old quiz questions, over homework questions as well. As for 5.5, I don't think I'm going to put that on the midterm. I think I'd rather wait and test on 5.5 on the final. So what we'll do is we'll have the midterm next week on Wednesday. We'll go on spring break, forget everything. Hopefully not, we won't forget everything, but try to remember as much as we can. Come back, and this will be our warm-up question, is example 6. This will kind of warm us up and remember how the heck did we do triple integrals. I see what example 6 is. Example 6 is where we actually, almost the same thing. Only now it's above a triangle. All right, so it's actually a little bit different. All right, in any case, we'll do example 6 as the very first thing that we do after spring break, and then I'll officially assign the homework for 5.5, and then it'll officially be fair game for a quiz, and of course it'll be on the final. But going over this stuff, one thing you can do, what I might do on the midterm, is give you a question about volumes. In fact, this problem right here, this last problem that we did, that could be a question that I asked on the midterm, because you could also set this up as a double integral with a top where you just integrate z minus x squared with respect to x and z. So some of these problems you can already do using just double integrals, but you also might be able to do them using triple integrals. So if you know the triple integral stuff, you're allowed to use that on the midterm to solve volume questions instead of using a double integral for volume questions. That's up to you. So, and let me know if you have any questions there. But I think that's it. I'm going to call that. Let's see, what else should I mention? Oh, on Moodle. If you go on Moodle, you'll have all the old quizzes. I've uploaded those. I've also uploaded some old exams. I make no warranty about whether the midterm is going to have anything to do with the types of questions I asked on my exams in my 2242 class last semester, but I wouldn't be surprised if there are some similarities. So if you are looking for more stuff to study, you can look at that. But remember, the order of operations for what you should study. First, study old quizzes. Second, study the problems that we did during lectures. And then third, look at the other homework problems that we had throughout the first half of the semester. And if you can do all that, you should do just fine on the midterm. All right, but I'm going to call this, I'm going to call it quits here. Y'all have a great day at UNC Charlotte. Thanks for watching, and we'll see each other in person on Monday.